Are you looking for an easy scaling solution for your software product? Do you want your system to handle peak load without spending a fortune on hardware? Do you also want to scale without massive redesign of the entire system? Well, message queues may just be the solution you need. In the next few minutes, we will go over the high-level architecture of message queues using a real-life example, explore the top 2 problems to apply the approach to, and discuss advantages and disadvantages of this kind of architecture. To understand how message queue architecture works, imagine that we are running a restaurant. There are 2 types of employees we have at this restaurant. We have waiters who get food orders from customers and deliver the cooked food. And we also have chefs who cook the food following the order that they receive from waiters. If we don't have any communication rules established between the 2 groups and just let waiters find and pick a chef to pass the orders to, it might work when our restaurant is small. However, as we grow the business with the increased number of customers and orders, we get to experience the following problems. First, waiters might spend a lot of time to find an available chef to pass their orders to. Second, waiters need to serve their current customer food before they move on to the next customer. And this, of course, increases the waiting time for the customers, who may just leave if no one takes their order for a while. And third, waiters also need to distract every chef every time a new order comes in, as they need to go and check with each chef if this particular chef is available to take the new order or not. In reality, no big restaurant works this way. Instead, a ticket queue system is typically implemented. Waiters write their orders on pieces of paper and attach these pieces of paper to a board. When chefs are done cooking their current meal, they take the next paper from the board in a first in, first out order to cook for the next customer. Such a system self-balances itself, as waiters no longer need to look for an available chef, and chefs look for the new orders only when they are available to take one. When the restaurant gets more customers and more orders than normal, this system functions just like it does with a small number of customers. Only the wait time for individual order gets longer. In a nutshell, this is the architecture pattern of message queue scaling. The waiters, the components that collect the requests, are called producers. The chefs, the components that pick up work and perform the actual execution, are called consumers. And in the middle, there is message queue component that accepts the messages from producers and waits until consumers become available to pick the messages up. Message queue architecture, unfortunately, is not applicable to every scaling problem. Specifically, when your customers need to get a response from your system within a short and predictable time span, you'd better use different scaling approaches. Let's look at the 2 general problems where scaling with message queues works the best. The first problem is offline processing. These are the scenarios when the process is initiated by schedule and doesn't have strict expectations on when they should be finished. A good example of such system is autopay that you probably set up for your electric and phone bill. The autopays are supposed to be processed once a month, and our customers don't really care about the specific time when the system gets it done. In order to protect your system from any scaling issues, you put all your autopay requests to the message queue and let the consumers to work on reading the autopay messages from the queue and extracting the payments for each of them. The second problem is async processing. For some scenarios in your software products, your customers don't expect the work to be done immediately. For example, when you upload a new video to TikTok or YouTube, you expect the processing to take a while, as the system on the other side needs to do a lot of work. It needs to store the video, it needs to check its integrity, and do all the other work necessary to start promoting the video. As a TikTok or YouTube system architect, You can put the requests to process new videos into a message queue to protect your system from overloads when too many new videos are being uploaded. Of course, for these scenarios, you should display a message to the users that their new videos are being processed and they should wait a while. As we just discussed, the main advantage of using message queues is to scale your system for the peak load without having to invest into machines to handle the maximum load. Message queues are also great at distributing the load between the consumers equally and ensure you don't have stale machines that are underloaded. The approach also naturally provides decoupling between producers and consumers, allowing them to be designed and implemented independently, as long as the messaging interface is established upfront. And lastly, modern message queues implementations also provide additional benefits, such as the ability to replay the failed messages and to guarantee the order in which messages are being processed. The main drawback of the architecture is the loss of predictability in the system. When a message is sent to the queue, there are no guarantees on how soon it will be picked up and processed. Message queues also add complexity to the overall architecture, as it is yet another component for engineers to integrate and maintain. The loss of predictability and the extra complexity usually leads to lower level of debuggability and traceability. It is harder to troubleshoot errors in a system that involves asynchronous processing with queues. While the queue-based architecture introduces redundancy for providers and consumers, the message queue itself oftentimes becomes a single point of failure. If you decide to use message queues for your products, you don't have to implement the queue by yourself. There are quite a few existing solutions on the market. The most popular ones are Apache Kafka, RabbitMQ, Amazon SQS, and IBM MQ. I hope you enjoyed this video and learned something that you can apply to your everyday work life as an engineer. Give us a like and subscribe, and we will see you in the next video.